Hello students! So this video here is on reflections and dilations with function notation, and it's a continuation of yesterday's lesson. Guys, in yesterday's lesson we did a sort of general overview about when you can expect to have reflections with your function notation, and again when you can expect to have those particular types of reflections, when you're going to have a vertical reflection, when you're going to have a horizontal reflection, and that we went into again. If that means when you're going to have a reflection over the x-axis or reflection over the y-axis, and we also talked about dilations in that previous video, where we talked about when it is that you're going to be expected to have a vertical dilation or a horizontal dilation based on the function notation, and we talked about when it is that you can expect to have a stretch or a shrink with either type of dilation, whether it's vertical or horizontal. So in this video, we're gonna kind of delve deeper into that, where we give you where I'm going to give you more examples. We're going to look at how these particular transformations look on graphs, where if you have to actually perform these transformations on graphs, we're going to do that, and we're also going to give you more examples of how they look when we're dealing with the function notation and with particular types of parent functions, with those types of parent functions that we've already kind of introduced you to. All right, so let's go ahead on and get started. First off, guys, do you remember this? You remember us talking about that function notation and how when you're using that function notation, and if there's adding or subtracting on the inside of the function or on the outside of the function, that the adding or subtracting part, or at least when your function changes by adding or subtracting a number inside or outside of the function, that represents translations. And did you remember again that again for this particular video, where we're continuing to talk about reflections and dilations, you remember that we said that again these transformations, reflections and dilations, only happen when you're multiplying, or when you're changing a function by multiplying a number on the outside or on the inside of the function. And again, that's when we're going to have reflections or dilations. And more specifically, do you remember us saying exactly when there will be a reflection? Again, so we're only going to have a reflection if the number being multiplied is negative. Again, it doesn't matter whether that number is multiplied on the outside or whether that number is multiplied on the inside. But again, if the function changes by multiplying some number on the outside of the function, or by multiplying some negative number on the inside of the function. So again, when you're multiplying the function times a negative number, is going to be a reflection. And then, guys, remember that we also said that it's only going to be a dilation if the number that you're multiplying by is not 1. In other words, if the absolute value of the number that you're multiplying by is not 1, that's the only time that you're going to have a dilation. Okay, so first we're going to take a closer look at reflections, and so we're going to look a little bit closer and delve deeper into reflections. Okay, so do you guys also remember us talking about this here in the previous video? Remember, we had said that specifically, in order for you to have a vertical reflection, which is, again, a vertical reflection is if a figure reflecting, or at least a vertical reflection, when we're talking about using this function notation, is reflecting over or about the x-axis. So again, that is reflecting over or about the x-axis. And remember, we talked about the fact that a vertical reflection only occurs if you're multiplying a negative number on the outside of the function, like what you see here with this general function notation, where you see the negative a times f of x. All right, and then guys, remember we talked about horizontal reflections and the fact that those horizontal reflections, when we are talking about this general form for the function notation, your horizontal reflections are going to be reflecting over the y-axis. And again, the only time that you're going to have a horizontal reflection with this particular general form for function notation is when you have some number that's multiplied on the inside of the function. So, guys, we're gonna take a look at some specific parent functions and how those functions will look as a result of doing these types of reflections. So again, we're going to look at specific examples or specific parent functions and how those functions will look after we have performed these vertical reflections and horizontal reflections. Okay, so guys, I've made this little chart for you here, and in this chart, we're focusing on the function notation for these specific types of reflections, and again, we're showing you with those six parent functions that I showed you in one of the previous videos. But again, so we're showing you with the absolute value parent function, and guys, if you're seeing like this little f with the little subscript of 1, that little subscript is there just to distinguish that it's different from these other ones. So f sub 1, f sub 2. Again, these are different functions, and I've just got that little subscript number there just to distinguish that they're different functions. Okay, so f1, f2, f3, f sub 4, f sub 5, f sub 6, right? Different functions. All right, or that the different functions have a different name. But anyway, so guys, you can see here that again, for the absolute value function, you can see the general function notation, negative f of x, where it's the negative, where it's some type of negative on the outside, and again we see that that's a reflection over the x-axis. And so guys, you can see what that looks like for each one of these different types of functions. For each one of the parent functions, you can see what the result looks like when we are multiplying or a negative number on the outside. Now again, the number for these right here that's multiplied on the outside is -1. But again, we do realize that it could be any negative number. But again, right here, the number that's multiplied in this chart is -1. But anyway, so again, you can see what that looks like for each specific parent function when you have a negative on the outside of the function, and it's going to be a reflection over the x-axis. Again, that's a vertical reflection over the x-axis. And again, it's a vertical reflection because the figure is going to flip up and down. It's going to sort of flip up and down over the x-axis. Then you see in the next column, that little general form where there's a negative inside of your function. And again, for that, where you're multiplying some negative number inside your function, we know that that's going to be a reflection about the y-axis. So, and again, that is a horizontal reflection. But again, that's going to be a reflection over the y-axis. And we say that it's a horizontal reflection because it's going to be, the figure is going to be flipping left and right. But it's going to be flipping left and right over the y-axis. Okay. But anyway, we can see what each of those equations look like as a result. Again, we can see what the parent function is, and we can see what the result is when we multiply a negative number inside of the function. So again, guys, notice that for the absolute value, when you're inside the function and it's negative inside the function, the negative is actually inside the absolute value signs with the x. For the quadratic function, notice how when you've got something inside the quadratic function, now they've got those parentheses there, right? And so it's letting you know that there's a change happening inside that quadratic function with the x, and they've got the parentheses there. Same thing with the cubic function. They're letting you know that there's some type of change happening inside of that function. And actually, and then with the square root, they've got the negative here inside the function with the x, and again with the square root or with the radical, you know that negative is inside the function because it is up under the radical with the x. Okay, again, and there you have a cube root, and you've got the negative inside of the cube root. Okay, same thing. And then, guys, so the last part with the reflection over the y-axis, you've got that negative as being inside of that exponential function. And again, guys, we know that the negative is inside of the function not only because of the parentheses, but again, guys, you really don't have to have the parentheses here. But we know that the negative is inside of this exponential function because that negative is a part of the exponent. The negative is a part of the exponent the same way that the x is an exponent, right? So there's a change that's happening inside of the function in the exponent right along with x. All right, and then, guys, in that last column is showing the function notation when there's both types of reflections. When there's a reflection over the x-axis as well as a reflection over the y-axis. So it's negative on the outside and it's negative on the inside. So, and again, guys, there's some number multiplied on the outside, some negative number multiplied on the outside, and some negative number multiplied on the inside. Again, in this particular chart, that negative number just so happens to be -1. But again, we know that it could be any negative number that's multiplied. All right, so again, it shows you in this column where it's negative on the outside and negative on the inside for each type of function. I hope that helps. Okay, so guys, we've got this coordinate plane here, and I've put a triangle up there, and we're going to call that triangle, we're going to call that f of x, right? We're going to let that be our parent function, and we're going to plot some specific reflections here. So let's plot and let's reflect that triangle, and let's do it as f of -x. All right. So you should be able to tell me whether or not this thing becoming negative on the inside, whether or not it's going to be a reflection over the x-axis or a reflection over the y-axis. So this thing right here, because it's multiplied by a negative number on the inside, is going to be a reflection over the y-axis. It's a horizontal reflection. So again, this triangle is going to either it's going to sort of flip either left or right, but that's going to be a reflection over the y-axis. So again, this is a reflection over the y-axis here. Alrighty. And so if we're going to do a reflection over the y-axis, then guys, what we need to do is we need to not only do we need to try to just reflect the whole triangle, and so we know that right now the parent function, this blue function, right now it's in the first quadrant. Now, if you don't remember your four quadrants, that's another little mini lesson. But anyway, we know right now this blue triangle is in the first quadrant. If we're going to reflect it over the y-axis, which is this vertical line here, then after it gets reflected over the y-axis, the new image for that is going to be in the second quadrant over here on the top left. Okay, and so guys, not only do we try to reflect the whole triangle, but guys, in order to do that, since we have like specific points here, you can see 3 specific points, right? Since we have like some specific points, we need to reflect each specific point over the y-axis. All right, so again, guys, we need to reflect each specific point over the y-axis. And so, guys, the way that we need to do that is the fact that guys, your pre-image. So let's take this point right here. Let me just kind of highlight exactly which point I'm talking about. Y'all see it? Let's take this point right here, and y'all can see that point that I got there. Okay, you should be able to see which one it is. I got it selected. All right, and so that point right now is at the ordered pair at the coordinate of 2, 3. All right, I'm going to unselect it. All right, so you see that point, 2, 3. If we were going to reflect that point over the y-axis, then guys, when we reflect that over the y-axis, guys, it needs to be the exact same distance away from that line of reflection. So it needs to be the exact same distance away from that y-axis when we flip it to the other side of the y-axis. So guys, here's the question. I'm going to select that point again so you can see it, right? How far away from the y-axis is this point right now? Exactly what distance away from the y-axis is that point right now? And you can count it, right? 1, 2, right? So that point is definitely 2 units to the right of the y-axis. So guys, if we want to reflect that over the y-axis, reflect that point right there. If we want to reflect it over the y-axis, then guys, we need to plot that point, or the new point for that. We need to plot it on the other side. And so guys, since this is a horizontal reflection, you're going to go again directly straight to the left. But when we do that, it's going to be the same distance. So when we plot this new point there, it's going to be, that's so sloppy, it's okay. There we go, that's better. It's going to be, again, that new point is going to be still 2 units to the left of the y-axis. Yeah, I want that to be black. Okay. Alright, so that will be where the new point will be for this one here. Okay, so that new point is going to be there. And so guys, when we get ready to when we get ready to reflect these other 2 points. All right, so this point right here, the point that's at 6, 6. So that is the point at the ordered pair 6, 6. And I've got it selected. I've got it highlighted where you can see it, right? So if we were going to reflect that point over the y-axis, then it would need the new point once we reflect it over the y-axis. The image of that point would have to be the same distance on the other side of the y-axis. So the question is, right now, how far is this point away from the y-axis? You should be able to tell me that. You should be able to, if nothing else, you can count it, right? 1, 2, 3, 4, 5, 6. So if this point is 6 points, 6 units away from the y-axis, then when we reflect it, it's going to have to be 6 units on the left side of the y-axis. All right? So when we reflect that, that's going to be 6 units on the left side there. Okay? So that's 1, 2, 3, 4, 5, 6. That it was 6 units on the right side, and now this new point, 1, 2, 3, 4, 5, 6, is 6 units on the left side away from there. So again, guys, there we have it there. All right, and then this last point here. If we want to reflect this last point over the y-axis, and again, I'm just showing you that again, really that to reflect the whole figure, you have to reflect each point. Again, I'm just showing you that. Okay. So again, this last point here, if we're going to reflect that over the y-axis, is when we reflect it over the y-axis, the new point is going to have to be the same distance on the other side of the y-axis. So right now, what exact distance away from the y-axis is this point? Okay, so this point is at the ordered pair of 8, 2. So again, right now, this point is 8 units away from the y-axis. So it's 8 units on the right side of the y-axis right now, and if we're going to reflect it to the other side of the y-axis, then the new point should also be 8 units on the 8 units to the left, or 8 units away from the y-axis when we plot the new point. If I can get that lined up, there we go. Trying to get that there. Close enough. All right. So that is where this thing will be, where each point there would be. All right. So and let me just count to make sure that's right. 1, 2, 3, 4, 5, 6, 7, and 8. Yes, 8 units away. 1, 2, 3, 4, 5, 6, 7, 8. Yes. All right. That is a perfect reflection over the y-axis. All right. So again, guys, that was a perfect reflection over the y-axis. And so we started off with just f of x, and we did that transformation with the f of negative x. And again, that was a reflection over the y-axis. And guys, remember that when you do that, and when you're reflecting it over the y-axis, that the pre-image and the image, when you're doing a reflection, the pre-image and the image should be the exact same distance away from the line of reflection. So again, you can see here that the pre-image and the image, or like for this point here, and for that point, the pre-image and the image are the exact same distance away from the y-axis. Same thing like for that one there, right? The pre-image there and the image here is the exact same distance away from that line of reflection. And the same thing for that third one, right? They're the exact same distance away from the line of reflection. All right, so guys, next we're going to plot the other type of reflection. Okay. Alright, so we're going to plot the function, oops, give me a sec here, negative f of x. Alright, so if we plot that negative f of x, remember guys that this is a reflection over the x-axis. Okay, so and we're talking about plotting a reflection using that same that same function f of x, using that same f of x function, okay, as the parent function. All right, so we're still talking about using f of x as the parent function here, okay. All right, so again, if we're still using f of x as the parent function, then we would need to take each point again, and this time we would need to reflect it over the x-axis, right? And make sure that it's the same distance away from that line of reflection. Make sure that when you plot the new point, it's the same distance away from the x-axis. So if we do that, so again, let's say we're doing this point right here. Then if we do that there, and let's see, the ordered pair for this point is 8, 2, right? 8, 2 is the ordered pair. The distance of that point away from the x-axis is 2 units, right? So if we're going to reflect this over the x-axis, then when we do that, it's going to be on the other side of the x-axis, and it's going to be the same distance of 2 units away. Okay, so that's going to be the new point for that one. All right, and then if we, okay, let's do this one here. All right, if we wanted to do this point here, right? Let's see, that ordered pair is 6, 6, and so the distance of that point away from the x-axis is 6 units. So again, if we want to reflect that over the x-axis, then we need to make sure that we go to the other side of the x-axis the exact same distance away. So we need to go 6 units on the other side of the x-axis. And like I said, guys, you can count that. Okay, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, right? Okay, so that's where the new point will be for that one. All right, and then this one here, the ordered pair for this point is 2, 3. So right now, this point is 3 units. The distance away from the x-axis, away from that line of reflection, is 3 units away from the x-axis. So we need to make sure that we, when we reflect it over the x-axis, it's on the other side of that, the exact same distance of 3 units away. Right there. 1, 2, 3. Okay? So again, if we want to reflect the whole figure, you need to reflect each point. Okay, so guys, that's those 2 reflections, and now we're going to look at what it would look like if you were asked to plot both reflections of that same parent function. If you were asked to do negative negative f of negative x, where it's negative on the inside and on the outside, where you're multiplying a negative number inside and outside. And so with this one, it's a reflection over both the x-axis and the y-axis. Over both the x-axis and the y-axis. Now, guys, thankfully, we've already done both of these, and so and let me explain what I mean. So, guys, when you're asked to do both over the x-axis and y-axis, you have to choose to do one of them first. So guys, again, when you're asked to do both, you have to choose and just pick which one you want to do first. So do one of these reflections first, and go ahead on and plot where those points are, or think about where those points are going to be. So do one transformation first, and then after you do that transformation, you're gonna have to take those new points and do the other reflection with those new points from the first one. So, in other words, it's like after you flip over one axis, you'll be in a new position, right? And then you're gonna do another flip from that new position. Okay. So again, I'm gonna do it as if I had made a reflection over the x-axis first, right? So if we had made a reflection over the x-axis, so this point here, it would have, again, if we had done a reflection over the x-axis first, right? This point would, it started off as being at the ordered pair of 8, 2. If we had done it over the x-axis first, it would have made its first jump to this point right here, right? So it would have made its first jump to right there, and after it was there, after that reflection over the x-axis, then we would need to make another reflection from this point. We would need to do a reflection over the y-axis. So if we were gonna, again, so we did the first reflection was over the x-axis from here to here, right? So now we're at a new position, but we're not done, because we still gotta do a reflection over the y-axis. So now from this new position, we do a reflection over the y-axis. So again, we have to go the same distance on the other side of the y-axis, and that will be a distance of 8 units away from the y-axis. So we have to go 8 units away from the y-axis over here. All right, and that would put that new point right there. 8 units away. Let me count, make sure. 1, 2, 3, 4, 5, 6, 7, 8. Boom. Got it, right? So that will put the new point right there. And that would be after a reflection over both axes. After a reflection over the y-axis and a reflection over the x-axis. All right, did you see the way I just moved my cursor? After a reflection over the y-axis, and after that a reflection over the x-axis. Boom, right? So you could do it. You could choose to do it either way. You could do it over the y-axis first. Okay, so look at what I'm doing. You could do it over the y-axis first, from there to there, and then do it over the x-axis, or you could do it over the x-axis first, from the parent function, over the x-axis first to there, and then over the y-axis. Either way, guys, regardless of which reflection you decide to do first, you're still going to end up having the same result afterwards. After you do both of them, you're still going to have that same result. Yeah. Okay. All right. That was that first point right here being reflected over both axes. Let's do this point. So again, if we reflect it over the y-axis, the new point will be there, and if we reflect this new point after doing the y-axis reflection, if we now do this new position over the x-axis, okay. So right now it's 3 units above the x-axis, and so if we reflect it over the x-axis from here, now the new point will be 3 units below the x-axis. All right. So this would be the new point, the new image for that pre-image there. After it gets reflected over both the x-axis, and then over the y-axis, All right. This point that I have selected right now is still going to be the image of this point. Okay, it's going to be the image after you do both reflections. Okay, all right, and then we've got this last point to go here. All right, so if we reflect this point over both axes, again, if you reflect it over the y-axis, it would be there, and then if you reflect it over the x-axis as well. So right now, this in its new position after the y-axis reflection, in this new position, it is 6 units above the x-axis. So we need to reflect it over the x-axis now. So if we reflect it over the x-axis, it's going to be the same distance away from the x-axis when we reflect it, 6 units on the other side of the x-axis. Okay, so after these 3 points are going to form the triangle. Of course, that is the new reflection, or after technically both reflections. All right, so that pretty much covers reflections. I do want to show you guys a little bit more about the dilations as well, and particularly how to determine what that scale factor is, and sort of how to use that scale factor, especially if you actually have to plot a dilation on like a graph. Okay, so guys, before we look at a few examples with dilations, let me just point out, guys, that every dilation has a scale factor. Guys, please remember that a scale factor determines precisely what factor the figure stretches or grows. It determines exactly, precisely by what factor the figure will stretch or shrink. Now, oh yeah, and guys, during my other videos where I mentioned dilation, I know I used other words for stretch and for shrink. Like for instance, I've used the word enlargement for stretching, and I know I've used the word reduction for shrink. Right? Some other words that they may use instead of stretch, they may use grow. They may say that the figure grows, and again, one word that they may use for shrink is compresses. The figure compresses, or the figure is compressed by a factor of such and such, right? So again, grow, of course, is to get bigger. Shrink or compress is, of course, to get smaller. So again, every dilation has a scale factor, and that scale factor determines precisely by what factor the figure is going to stretch or shrink, guys. And again, I just wanted to make sure that I mentioned those words, grow and compress, that I neglected to mention in the previous videos. Those are other words that are used in place of stretch and shrink. Okay, so guys, again, for vertical dilations, whether it's a stretch or a shrink, for vertical dilations, guys, the scale factor is going to be pretty much straightforward. The scale factor is going to be whatever that number is that's being multiplied on the outside. So, like where you see the A here, the A that's being multiplied on the outside of this form, whether that A is positive or negative, the scale factor is going to be the absolute value of that number. What does that mean? That means that let's say that number was 5, right? Then the absolute value of 5 is 5, right? Let's say that number was -5. Then the absolute value of -5 is 5. So again, guys, whatever that number is on the outside, whether it's positive or whether it's negative, then the scale factor is going to be the absolute value of that number. I'm going to erase this because we should know how to find the absolute value of a number. If not, pick up a scientific calculator or a graphing calculator and you can find the absolute value of something. But anyway, I'm confident that you guys can do that absolute value. Anyway, for horizontal dilations, those are ones where you are multiplying some number on the inside of the function with x. The scale factor for horizontal dilations is going to be counterintuitive in a way that seems almost unnatural. So again, the scale factor is going to be the reciprocal of whatever that number is. And here where I've got 1 over b or 1 divided by b written, that's how we write out the reciprocal. Again, the scale factor is going to be the absolute value of the reciprocal of whatever that number is. And if you guys don't remember like what reciprocals are, for instance, for instance, guys, as far as reciprocals are concerned, for those who need a little refresher on numbers that are reciprocals. For instance, 3 is a reciprocal of 1/3, right? For instance, 2/5 is a reciprocal of 5/2, right? 1/8 or whatever is the reciprocal of 8, right? So reciprocals, in other words, where you flip the fraction, right? In other words, you flip the fraction, all right? But again, for a whole number, if you got a whole number, then the reciprocal of that is going to be 1 over that number, like 3 and 1/3. Anyway, that's a little refresher, reminder about reciprocals. I'm going to erase that. All right. Okay, so guys, I've made these tables here to show you different examples of vertical dilations and horizontal dilations, and I've made them specifically with those parent functions that we had discussed and in one of the previous videos. So again, guys, here we've got those 6 parent functions that we had discussed in the previous video. So in this chart that's on the right, in this chart that's on the left here, we can see that it's got vertical stretch and vertical shrinks. Again, guys, the scale factor for these vertical dilations is pretty much going to be straightforward. And again, guys, remember that for a vertical stretch or a vertical shrink, it is going to affect your y values, right? So what am I saying? If a vertical stretch is going to affect your y values, that means that if the scale factor is 3 for a vertical stretch, that means that your y values will grow by a factor of 3. Right? So whatever your y values are, if your scale factor is 3 for a vertical stretch, then your y values will grow by a factor of 3. What does that mean? Whatever the y value is, you multiply it times 3. So if the y value for certain points, if the y value was 2 for a certain point, you'll multiply that y value times 3. And then the y value, the new y value, will be 6 instead of it being 2. And that's how it becomes a vertical stretch. But anyway, guys, again, you can see here for each of these results, or for each of the equations that have a result for the vertical stretch here, you can see that again, that number is being multiplied on the outside of the function. On the outside of the function. So you can see how the parent function looks and how it looks when you've got that number being multiplied on the outside, the 3 being multiplied on the outside for this vertical stretch column here. And then you can see how each of these parent functions will look after a vertical shrink. After a vertical shrink. So if it was being shrunk by a factor of 1/4, again, that means that the scale factor is 1/4, and the number on the outside of that's being multiplied on the outside there, like I said, and guys, it could be a positive 1/4 or it could be a negative 1/4 that's being multiplied. But again, here I've just got positive 1/4. But again, the number in these equations, that number could be positive 1/4 or it could be negative 1/4. The same thing with the 3 here. It could be positive 3 or it could be negative 3. Again, I just put it as a positive here. All right, but anyway, the scale factor would be 1/4 for the vertical shrink. The scale factor would be 3 for the vertical stretch. Okay, that's the vertical dilations. For the horizontal dilations, guys, again, as you see here, the scale factor for horizontal dilations is counterintuitive. So you can see here that for horizontal stretch, look at the number that's being multiplied here for a horizontal stretch. For this particular, in these examples, I've got a 1/3 that's being multiplied on the inside of the function. Multiplying something times 1/3 is going to be a horizontal stretch. That don't even sound right. Multiplying something times 1/3 is going to be a horizontal stretch. Yeah, that technically that sounds like it should be wrong. But again, guys, I've told you that with horizontal transformations is going to seem counterintuitive, and it's going to sort of be the opposite of what you would expect it to be. So yes, for a horizontal stretch, it is okay for the inside here to be multiplied times 1/3, and it still be a horizontal stretch. Okay. All right. So you can see here each of these functions, each of the results. You can see the equations here after we have done a horizontal stretch, and you can see exactly what they should look like, with the 1/3 being multiplied on the inside of each of these functions. And then, guys, you can see this last column here for the horizontal shrink, where we have the inside here being multiplied times 4. And again, the scale factor is the reciprocal of that number. Again, here, even though the inside is being multiplied times 4, the scale factor is the reciprocal of that. And again, it's being multiplied by 4, but it is a horizontal shrink. Okay, and the inside is being multiplied by 4. We can see what the equation looks like after there's a horizontal shrink by a factor of 1/4 here, where we're multiplying the inside of these functions by 4. And you can see how each of these equations will look afterwards. Okay, so guys, next I'm going to briefly show you, just briefly, very briefly, show you how to do these delta math assignments. Okay, delta math assignments, here we come. And again, this is for the students who are enrolled in my classes at our school. Delta math, show you how to do those. Okay, so guys, one of your delta math assignments for today's practice and lesson is asking you to reflect the figure over a certain line. Now, again, guys, this is not the same. This is not the same thing as the function notation. Guys, for the function notation that we've gone over with reflections, the function notation only covers reflecting it over the y-axis or reflecting it over the x-axis. But again, guys, it doesn't have to be the y-axis and the x-axis that is being reflected over. It can be reflected over any vertical line, like they're asking you to do here, over the line x equals -2, right? And it can be reflected over any horizontal line. And I will find one where they're asking you to do it reflect it over a horizontal line as well. But so, guys, again, here they ask you to reflect this figure over this vertical line, this blue vertical line that you see right here. So, guys, they're saying plot all of the points of the reflected figure. So, again, as I mentioned before, guys, and I actually showed you something similar to this again in this video earlier. But so if you want to reflect this figure over this vertical line, you're going to have to reflect each point over this vertical line. Again, guys, so for whatever point that you're reflecting, make sure that when you reflect it over this line, that the new point is going to be the same distance away from that line of reflection. So you guys can see where my mouse is, right? You can see where that point is. This point is 2 units away from the line of reflection. So when I reflect it over, I'm going to put it 2 units away from the line of reflection on the other side. And all I have to do to put it there is click exactly in the place where I want it to be, where I need it to be. All right, now you can see where my mouse is right here, right? I hope so. If not, oh well, I don't know. I don't know what to tell you. But I hope you can see where my mouse is. So this point right here. Now, what happens if you make a mistake and click the wrong point? It says you may click a plotted point to delete it. I just clicked the wrong point. Well, guess what? I'm going to click it to delete it. All right. You don't have to be stuck with it, right? So now, if I want to reflect this point over, it's 1 unit away from the line of reflection, and when I reflect it to the other side of that line of reflection, it needs to be 1 unit away. And then we're going to do that for each of these points. This one is 5 units away, so we want to make sure that when we reflect it, we put it 5 units away on the other side. And again, guys, you can count. You can count how far away it is to make sure that you're doing it the same distance. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Again. All right. This one is 4 units away. Reflect it over, 4 units away. This one here is 7 units away. So when I reflect it over, 7 units. Yeah. Let me count that. 1, 2, 3, 4, 5, 6, 7. And let me count this. 1, 2, 3, 4, 5, 6, 7. Good. Let me count that. 1, 2, 3, 4. And 1, 2, 3, 4. Good. 1, 2, 1, 2. 1, 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. That should be correct. I'm not even going to click submit. But again, if you need to delete a point or plot something, if you figure that something's wrong and you need to replot one of those points, okay, just click on it to delete it and put it where it needs to be. If you put it again where it needs to be. All right, that should be that reflection. I'm going I'm going to just show you real quick what it would look like if it was a reflection over a horizontal line. Okay, so this one here is asking you to reflect this figure over this line, over the horizontal line, y equals 2. And again, we haven't necessarily gone over, well, I don't recall, I might have mentioned it before. The reason why the equation of this horizontal line is y equals 2 is because every single point on this line, every single point on that horizontal line has the same y value, and every point on this horizontal line has the y value of 2. So that's why the equation of the horizontal line is y equals 2, and it's a similar reason for why the equation of a vertical line is x equals some number. But anyway, all right. So again, guys, if you want to reflect this over this horizontal line, reflect each point over it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Reflect each point over it. 5, 5. Okay. Boom. Just like that. All right. So, guys, this problem set here is another problem set that you'll have to do in today's lesson on Delta Math. For this problem set, it is asking you to reflect this function. And guys, for this one, or for a type like this, you're going to have to click and drag. Click, drag, and hold, or click, hold, and drag, right? And so, guys, I've mentioned in the previous videos that when you have to click and drag on these Delta Math assignments, that if you're using your cell phone to do it, and you're on your cell phone internet browser, that it's going to be easier for you to do this if you change that internet browser or change the site to a desktop version or to a desktop mode. Change that website to a desktop mode or desktop version on your internet browser on your phone, and that's going to make clicking and dragging this a lot easier. Anyway, so guys, if you're going to reflect this, first off, you need to make sure that you know exactly what type of reflection is happening here based on this equation. So, guys, this equation here is a cubic function, and again, for this cubic function, it's negative on the inside. So, guys, since it's multiplied times a negative number on the inside, then this is going to be some type of horizontal change because the change is happening on the inside. So it's going to be, guys, a reflection that happens horizontally. And so if you see the way my mouse is moving left and right, if you got a reflection that's happening horizontally, that's going to be, especially for this function notation, that's going to be a reflection over the y-axis. And again, I've explained that in this video earlier. That again, when it looks like this, and I've even put a nice looking chart in there for you, so that when it looks like this, that it will be a reflection over the y-axis. But anyway, guys, if you want to do that for this particular thing, now when you were doing a similar looking exercise where it was translations, listen, when you were doing translations, I told you to click, drag, and hold the green dot. Guys, we are not doing translations here. So please do not, I repeat, do not please do not click and drag the green dot, because if you do, it is going to translate and it's going to shift the position of where this figure is, and you're not asked to translate anything here. So do not click and drag the green dot. So guys, you can click and drag, and really you only need to do it with one of these dots. So guys, pick one of the other dots, and it looks like this is blue or purple. I can't really tell Yeah, I guess my eyes are just tired right now. But you're going to click, drag, and hold, and you only have to do it with one of these dots. I'm going to choose this one right here and reflect, and just put one of these dots where it should be if you're going to reflect it over the y-axis. This one here is over the y-axis. Make sure that you know and that you're doing it over the right axis. Okay? All right, so let me start that back over. That was where the point was originally, right? If I'm going to reflect it over the y-axis, I'm going to click, hold, and drag it this way across the y-axis, and it needs to be the same distance that it was. It was 1 unit. It was 1 unit over there. It was right there, 1 unit. And now it should be in the right place. And you can see that now it's been reflected over the y-axis. Okay? Just to show you it is correct. Okay? Alright. I'm going to... Guys, it would work in a similar way if this was reflecting it over the x-axis. Alright, so again guys, this here is reflecting it over the y-axis. It would work in a similar way if you were reflecting it over the x-axis. And so guys, if you were reflecting it over the x-axis, then it would have, or this equation would have a negative on the outside of this function, instead of a negative on the inside. But again, we'll show you if some of these other types are, or some of these other types of problem sets are different. I'm going to show you that. Let me check on that real quick. Of course we had some other different types of problem sets, because the first two types of problem sets that I just showed you were on reflections. And again, we talked about not only reflections, we talked about dilations in this video lesson too. So this particular problem set, this one says level 1. If I'm not mistaken, I think I've browsed through enough of these types on this particular problem set to know and be able to tell you that this problem set where it says level 1, I believe is only on vertical dilations. But again, guys, you should be able to look at the equation and tell. Again, this equation here is a absolute value equation, and you should be able to look and tell that there's a number being multiplied on the outside of this function. And again, if there's a number multiplied on the outside, that means there's a change outside of the function that's happening, which means it's a vertical change. So, and because you're multiplying the number, this is going to be a dilation. So guys, remember that if it is a vertical dilation, you need to determine whether or not this vertical dilation is a stretch or a shrink. Again, guys, I've tried to show you earlier in this video when or how the equations will look when you have a vertical stretch or a vertical shrink. But again, guys, because this number that we're multiplying on the outside of this function is bigger than 1, because this number is bigger than 1, this will be a vertical stretch. Okay? So it's going to be a vertical stretch by a scale factor of 2. So again, guys, here is a vertical stretch and the scale factor is 2. What does that mean, guys? If the scale factor here is 2, that means that the y values are going to be affected. So guys, the y values are going to be pretty much multiplied by 2. And so let me show you. Again, guys, I mentioned in that last little exercise that we do not, I repeat, we do not want to move the green dot because we are not translating. We are not doing any shifts. So please do not move the green dot if you're asked to dilate. All right, you're going to want to choose just one of these other points. Again, I'm just going to, you see where my mouse is, right? I'm just going to choose this point right here. And for this point, guys, the y value of this point, you should be able to look at a certain point and tell what the y value of that point is. The y value of this point right now is 1, right? So if the original y value for this point is 1, if we're going to do a vertical stretch by 2, where we're using that scale factor of 2, so when we stretch this, the y value is no longer going to be 1, but we're gonna stretch the y value by a factor of 2, meaning that what happens when you multiply it? When you multiply the y value 1, when you multiply that times 2. When you multiply 1 times 2 for the y value, you get 2 as the new y value, right? So guys, when you move this point, because this is a click and drag, when you move this particular point here and to vertically stretch it, instead of the y value being 1, you're gonna move it either up or down, right? But again, instead of the y value being 1, we're going to move the y value up by a factor of 2, meaning that, again, now instead of the y value being 1, we have clicked and dragged it, and we have made this y value be 2. All right, so let me start that over again. All right, I chose this point. So if I wanted to do this point, and it's a scale factor of 2, and it's a vertical stretch with a scale factor of 2, instead of the y value staying here at 1 for this point, I'm going to click and drag it and make the y value for this point 2. You guys see that? It's been a vertical stretch. You see that, right? Let me start it over. Let me show you with a different point, just to let you know you can do it with any point, right? So if I was gonna, you see where my mouse pointer is, right? On this point here that has the y value 4. If I was going to do that same stretch, or same stretch by a factor of 2, instead of the y value staying here at 4 for this point, what happens if you stretch the y value by 2, or in other words, multiply that y value by 2? Instead of the y value being 4, if we multiply 4 times 2, then the new y value, when we stretch it by a factor of 2, is going to be 8, right? Because when we multiply the y value of 4 times 8, when we multiply the y value of 4 times 2, we get 8. So if we stretch this, instead of the y value staying at 4, now the y value is going to be 8. So where the original y value for this point was 4, if we click and drag it and move it, now the new y value for that point is 8. Okay? Alrighty. That's how you do a type of problem like that with the click and drag with the dilation. I'm going to find one. Where it's a shrink, a vertical shrink as well, and show you that really quick. First off, let me just show you that Mr. Starkey know what he's talking about. Correct. Multiply the y values by 2. You see that? So instead of the y value being 1 there, we clicked it and we moved it so that the y value was 2. If we had done it for this point, instead of the y value being 2, if we multiplied it by, instead of the y value being 2, you could have clicked and dragged this point up here so that it had the y value of 4. Again, guys, Starkey knows what we're talking about. All right, I'm going to find a problem where it's a vertical shrink, just to show you really briefly. Okay, so guys, this one here is a vertical shrink, and we know it's a vertical shrink because you're multiplying a 1/8. This number that we're multiplying on the outside here is smaller than 1. Again, guys, they could have made this number negative 1/8. It would still be a vertical shrink, even if this number was negative 1/8. But anyway, if it was negative 1/8, not only would it be a vertical shrink by 1/8, but it would also be a reflection. But anyway, so guys, now you again, just like with the last point, you need to pick one point to do this with. Now, Guys, I'm not going to pick this point that has the y value of 1. Why am I not going to pick that point? Because, guys, it would be extremely difficult to actually click and drag this thing and actually get it to a place where the y value, where the new y value would be 1/8, right? Yeah, that would be tough to do with a y value of 1. But guys, if you look here, you can see that there is a point that has a y value of 8, right? So this point right here does have a y value of 8. And if you multiply this y value times 1/8, and if you shrunk it by a factor of 1/8, then the new y value here, instead of it staying at 8, if you multiply 8 times 1/8, the new y value is going to be 1 for this point. So if we click and drag this point using that scale factor of 1/8, again, it changes the y value from 8. And if we scale it down on a factor of 1/8, multiplying that 8 times 1/8, then we get the new y value. It should be 1. So I'm going to start shrinking this on down using that. The new y value here should be 1, right? Boom. So the y value of this point went from 8 to 1. It was a vertical shrink by a scale factor of 1/8. Let me submit this. Let me just show you that Mr. Starkey know what he's talking about. Right? Mr. Starkey know what he's talking about, okay? Again, guys, you multiply your y coordinate by 1/8. Again, folks, if possible, and it should be possible for you to find a point where when you multiply it times that fraction is going to give you a whole number. Again, guys, I chose to use that point that had a y value of 8, because I knew if I multiplied that y value of 8 times 1/8, it would give me a whole number. Okay, so I chose to move that one to right here. All right. Next up, guys, I think the last problem set is with horizontal dilations. And I just want to show you that very briefly, and then we're going to call it quits because it's very, very late here. Okay, so guys, this problem set here is, and this one here is similar to the last one, but in this one, we've got to do a horizontal dilation. We know it's a horizontal dilation because you've got some number being multiplied on the inside of the function. And again, I've tried to show you several examples earlier in this video, even made nice little charts for you, showing you with different parent functions how the equation looks when you have a horizontal dilation, either a stretch or a shrink. All right, so guys, for this particular horizontal dilation, this one is going to be a horizontal stretch. Yes, this is going to be a horizontal stretch. How do we know that? Because it's counterintuitive for these horizontal transformations. And again, I told you that the scale factor for horizontal dilations is going to be the reciprocal of that number that's being multiplied there. So guys, the reciprocal of this number 1/4, the reciprocal of 1/4 is 4. So guys, the scale factor here is 4. So again, guys, this is a horizontal stretch by a scale factor of 4. So again, here we've got a horizontal stretch by a scale factor of 4. So again, folks, if you're going to do that, these horizontal dilations are going to affect your x values. So guys, for this, I suggest that again that you focus on the x value. So if the scale factor for this one is 4, right? Then you're going to have to and again, guys, just choose one point. One point. I'm going to choose this one here. You see where my mouse pointer, where my cursor is, right? I'm choosing this one. So if the scale factor is 4, then you need to take the x value here, the x value, and you need to multiply that x value times the scale factor 4. So again, the x value for this point where my mouse cursor is, and I'm on a point that has an x value of 1. So if I use the scale factor of 4, okay, it's going to be a horizontal stretch using a scale factor of 4, right? So if I multiply the x value 1, if I multiply that times 4, instead of my x value staying here at 1, I'm going to click, hold, and drag it, and I'm going to move it, right? Instead of the x value staying here at 1, I'm going to do a horizontal stretch using the scale factor of 4. So my x value is going to change from 1 to 4. And you can see here that now, instead of the x value for that point being 1, it is now, that x value is now 4. Let me start that over. Let me show you again. The x value was 1 here, right? And if I move that point where the new x value is multiplied by 4. So instead of it being the x value 1, the x value is 4. Let me just show you that Mr. Starkey know what he's talking about. Correct. Right? So again, you multiply the x values, the x coordinates, by 4. And guys, you didn't have to use that point that I used. You could have used any other point besides the vertex of this one, besides that green dot. Okay? You could have used any of the other points besides that green dot. All right. Folks, that's it. This one was a horizontal stretch. I'm not going to show you a type of problem where it's a horizontal shrink, but again, actually I am. I take that back really quickly, I am.